I'll explain the Unitree G1 as if I were standing on stage giving a single continuous expert presentation, one flowing explanation that follows your requested order from origins through future impact, touching both headline specs and the less obvious details, and citing primary sources where useful. The Unitree G1 was created by Unitree Robotics, the Hangzhou-based firm founded by Wang Xingxing, doing business as Hangzhou Yushu Technology Company Limited, which built a consumer and research-focused robotics product line that began with quadrupeds like Go1 and progressed into bipedal humanoids. Unitree's engineering and product teams led the G1 development as an evolution of earlier humanoid work H1 and the company's experience in motors, control and perception. The G1's invention and public introduction came in 2024. Unitree unveiled the G1 as an upgraded, production-oriented humanoid platform presented around robotics conferences and in press releases in mid-2024, positioning it as a compact, agile humanoid intended for research, education and applied use cases rather than as an immediate household servant. That 2024 launch followed the H1 prototype work and a series of demonstration videos showing dynamic motions, and Unitree published product pages and press materials describing the machine's capabilities soon after the reveal. At a glance, the main features and specifications that define the G1 are its size and payload envelope, joint count and motion capability, onboard computing and perception suite, endurance, and the dexterity of its hands. Unitree describes the G1 as roughly 127 centimeters tall and about 35 kilograms in weight. Battery included brings the operating weight higher in some listings, with a walking speed capability around 2 meters per second and large joint movement ranges. The platform is offered with configurations ranging from about 23 to 43 motorized joints depending on the package and whether dexterous hands are included. The G1 boasts high peak joint torques. Unitree quotes figures up to the order of 100 plus Nm for some actuators in marketing material, force position hybrid control for manipulation, a 9000 mAh quick-release smart battery with roughly 2 hours of runtime under certain operating modes, and built-in audio, speaker and 4-mic array. For vision and sensing it offers depth cameras and a 3D lidar option, plus standard connectivity like Wi-Fi 6 and Bluetooth 5.2. Compute options include a high-performance module such as an NVIDIA Jetson Orin or equivalent 100 TOPS unit depending on SKU. Physically, the G1's body structure is compact and engineered for a mix of dynamic motion and manipulation. Unitree's marketing and product pages describe a modular mechanical architecture with hollow joint routing for electrical cabling, brushless or gear-type joint motors at each degree of freedom, and multi-link limbs tuned for both stability and large joint angle ranges. The outer shell and limb covers are typically lightweight composites and plastics for impact resistance and serviceability, while internal frames and gearbox housings use aluminum alloys and other metal structural components where stiffness is critical. The hands, when present, use multi-joint fingers with force sensors and compliant elements to enable dexterous grasping. The design emphasis is on a balance of stiffness for dynamic moves and compliance for safe interaction. Unitree also stresses quick-release battery packs and modular accessory mounting to adapt the platform for different research tasks. Under the hood, the G1 combines classic robotic subsystems, powerful actuators, sensors for perception and proprioception, a real-time control stack, and higher-level AI for planning and learning. Its actuators are position-torque-capable joint motors with encoders and sometimes dual encoder redundancy. Control uses force-position hybrid strategies to allow both precise motion and compliant force control during manipulation. Sensors include inertial measurement units (IMUs) for balance, joint encoders for position and velocity, depth cameras e.g., Intel RealSense family referenced in some reports, Livox or similar lidar for 3D mapping, and microphone arrays for audio input. The robot runs onboard compute for low-latency real-time control, dedicated controllers, and higher-capacity modules e.g., NVIDIA Jetson Orin or Unitree's 100 TOPS compute option to host perception stacks, neural networks, and imitation reinforcement learning models. Unitree also promotes a robot world model, an imitation plus reinforcement learning workflows robot unified large model to accelerate task learning. The software stack exposes APIs and secondary development support for researchers to train policies and fine-tune behaviors. In practice, walking, balance, and dynamic maneuvers are handled by real-time controllers while vision and task planners run at higher levels, and actuator torque control plus sensory feedback enable manipulation tasks. On price. When Unitree launched the G1 in 2024, it publicly indicated a price point around $16,000 for certain ADU or base configurations, making it far cheaper than many industrial humanoids and positioning it as an accessible R&D platform. Reseller listings and bundles have shown variation, with some retailers listing higher prices once shipping, duties and optional modules are added, so you'll see values from approximately $16,000 up toward the mid-$20,000 range depending on options and region. It's also important to note that Unitree later introduced other bipedal models with different price points, e.g., an R1 model announced at a much lower starting price, which demonstrates ongoing product diversification and affects the relative value picture. Unitree is a Chinese company and the G1 is manufactured and designed out of China, Hangzhou. The corporate lineage, R&D centers and much of the supply chain are China-based, while the company sells globally through direct channels and international resellers. Looking forward, the G1 and platforms like it have several tangible benefits and applications for humanity. They provide affordable humanoid research platforms for universities and labs to explore human-robot interaction and manipulation. They can accelerate development of assistive robotics for healthcare, rehabilitation, and elder care. They serve as testbeds for household task automation, making breakfast, tidying, simple cooking maneuvers when combined with advanced perception and learning, and they'll likely be used in public service domains such as inspection, logistics in constrained environments, education and entertainment. Importantly, more affordable humanoid platforms democratize access to hands-on research in whole-body control, which historically has required very expensive hardware. There are also hidden or less-known facts worth flagging. Unitree's move into humanoids builds directly on lessons learned from their quadruped line Go 1, Alien Go, etc., so many control and motor design choices are adaptations rather than ground-up reinventions. Some of Unitree's marketing numbers, e.g., top torque or sprint speeds, depend heavily on configuration and test conditions. The modular offering 23 to 43 joints means two buyers can have significantly different capabilities even though the product name is the same. And the hands, while dexterous for demonstrations like soldering or flipping food, still require substantial task-specific training and are not plug-and-play for arbitrary household chores. Also, because Unitree targets research and education, buyers should expect to be doing their own software work to achieve higher-level autonomy. Finally, possible future developments and impacts. Technically, we'll see continual improvements in onboard compute and perception, better multimodal large models running on device, increases in joint torque density and battery energy density that improve endurance and payload, and tighter integration of learned policies so humanoids move from scripted demos to more generalizable everyday skills. Economically and socially, continued cost reductions, as seen with subsequent lower-priced models from Unitree, could put humanoid platforms into more labs, small businesses, and creative industries, accelerating innovation but also raising questions about regulation, safety standards, and workforce effects. If imitation learning, transfer learning and multimodal LLMs onboard become robust, the practical utility of humanoids in caregiving, manufacturing in human-centric spaces, and hazardous environment mitigation could expand dramatically. Conversely, realistic concerns around safety, privacy, and misuse will require concurrent policy and design standards as these robots enter public spaces.